This video will look at bond length and bond energy. Bond length is described as the distance between two nuclei that are bonded together. This chart gives me a couple bonds to look at. For example, let's say we draw kind of a diagram of a hydrogen-hydrogen bond. Hydrogen's a pretty small atom. We'll make just a little baby atom. There we go. The distance between the two nuclei, that's like the bond length. So it's very much affected by the size or the radius of the atom. If I have small atoms like hydrogen, hydrogen, the bond length is small. Another small atom on this chart might be fluorine. Now fluorine's probably a little bit bigger than hydrogen. Fluorine has its electrons in two energy levels. Hydrogen is only looking to fill the first energy level. But as I go across the group, fluorine should be one of the smallest elements of the second period. So let's draw atoms that are maybe a little bit bigger than hydrogen, but still relatively small. Distance between the two nuclei. Here might be my fluorine-fluorine bond length. And again, I can look at this chart and it kind of makes sense. They're giving me bond length measurements in units of picometers. PM stands for picometer, not nighttime. And so as I look at the bond length, the fluorine-fluorine bond length is a little bit larger than the hydrogen-hydrogen bond length. Well, the atoms are a little bit larger. Now look what happens as you go down the halogens. From fluorine to chlorine, bromine, iodine. Do you notice how the bond lengths continue to increase? Well, it's because the atoms get bigger going down a group. So by the time you get down to iodine, here's maybe my giant iodine atoms. Iodine, oh boy, iodine. Those are big atoms, so they're going to have a large bond length. Okay, so bond length very much related to the size of the atom or its radius. Why do we care? We care because it relates to bond energy. This bond energy is described as energy required to break a bond. Now, one of the most important things here is that energy is required to break a bond. These atoms want to be bonded. That's how they get their full octets and become very stable. If you want to break a bond, then you must add energy. These particles are very much attracted to each other and happy in the bond, stable in the bond. Energy is required to break the bond. Energy is released when the bond forms. Then the atoms are at a lower, more stable energy level. So this bond energy is a measure of how much energy is required to break that particular bond. It's in units of kilojoules per mole. Well, kilojoules is a pretty common unit of energy, and the MOL, mole, is a unit that we'll talk much more about third quarter, but it's a measure of number of particles or number of bonds. So let's see what happens here if I compare maybe like the fluorine down to the iodine. Fluorine had the smallest bond length, but of these halogens, it has the largest bond energy. Oh yeah, well this kind of makes some sense. If you have a small bond length, the atoms are closer to each other. The positive nuclei are closer to the negative electrons, which creates more attraction between those atoms. If there's more attraction between the atoms, it's going to take more energy to break that bond. So the smaller atoms, the smaller radii, with their nuclei closer to the negative electrons, create more attractive forces, meaning more energy required to break those bonds. But then on the flip side, this makes sense. As I have larger atoms like the iodine, the nuclei are further from the negative electrons, so there would be less attraction between the atoms with large bond lengths, meaning less energy required to break the bond. So that iodine bond has the smallest bond length on this chart. Obviously, we don't have every possible bond on here, but it shows the general trend. And they also have hydrogen chlorine and hydrogen iodine. They both have hydrogen, so the difference is the chlorine versus the iodine. Chlorine is a smaller atom, so the bond length is smaller in the hydrogen-chlorine bond, but then the bond energy is larger than the hydrogen-iodine bond. So bond energy, the energy required to break the bond, is very much related to the size of the atom. There's one other factor that will affect the strength of a bond, or the amount of energy required to break the bond, and that's whether the bond is single, double, or triple. And we'll look at that in one of the next videos.